Good afternoon to our respected director, distinguished faculty members, guests from across the globe, and all the students. I am Maithili Gosavi, a student of FYMCA. We have already had a morning full of brilliant discussions, and the momentum is only growing. We are about to connect with industry giants and academic leaders from Australia to the UK. So I hope you all are as excited as I am to learn from the best in the business. Let's dive right into our next session. To lead us into our final session, we are going virtual all the way to Australia. It is my pleasure to introduce Mr. Connor MacDonald, sir. His session, AI Seems Like Magic, the Fundamentals for the Novice, is perfect for us students. Our next speaker's journey began with a challenge of single kilobyte of RAM, fueling a lifelong passion for data and database development. Today, he is a world renowned expert in SQL and Oracle databases. With a career spanning decades, he has shared his expertise at over 150 conferences globally. Beyond the stage, he is a dedicated mentor to the developer community, serving as a key contributor to Stack Overflow and Ask Tom. Today, he joins us to demystify the magic of AI, breaking down complex concepts like LLMs and vectors into practical fundamentals for the Oracle database. Please join me in welcoming a true master of clarity, Mr. Connor MacDonald, sir, to help us find the logic behind the magic.
Thank you very much. Hopefully you can see me and hear me and see my slides, etc. Sing out on the chat line, or the organizers can if you can't, but hopefully we've got everything in readiness. For me, it's late in the afternoon, but I'm sure you've just probably had a wonderful lunch. One of the reasons I always say I could never live in India is because the food is too good, and I would be just have a huge stomach within no time. So I was in India in February, hope to be back there in July, but in the interim, we'll do something virtually. So my talk today is AI for the total newbie. If you're experienced with artificial intelligence, then maybe this is not the talk for you, but I've been doing this at various places around the world, mainly for both at the people at the student level like yourselves, but also for people who are experienced professionals but are just getting into the AI element. If after this session you have questions, you can always reach out to me. That QR code on the screen, even with my ugly face in the middle of it, will actually work. It'll take you to linktree/Connor, which is where you can get all the various ways of getting in touch with me. Alternatively, you can hit my blog, which is connormacdonald.com. I've got a YouTube channel, and you can obviously, you're welcome to hit up me on LinkedIn. So I need to be honest here. This is fundamentally about ego. And before 2023, I had been working in the IT profession for about 30 years. And so I knew a lot of stuff. I sort of had a healthy ego for all the knowledge I had. It was a good place to be. People would come to me to ask for advice. I would speak at conferences, etc. I felt very good about myself. And then it all changed at the end of 2023 when ChatGPT came along, because all of a sudden there were all these new terminologies, new acronyms, new things that I had never heard about before. So all of a sudden I'd gone from being a database, sort of very well qualified database practitioner to being a total novice, all thanks to something like AI. So I figured, why not sort of share that journey of being a newbie in the AI world and share that with people, because I'm sure there are others like us. And for many of us, this challenge is the same. AI has been such a rapidly adopted, fast thing that we sort of struggle to try keep up. So this is all about, my journey, that the basics of artificial intelligence, where it came from. This is not about, basically using Claude or Codex to do, multi-sub agent, coding, etc. That's for other talks on other days. This is a very much a journey back into very much the fundamentals. So hopefully you'll get something out of it as well. All of this starts with a very simple conversation around a thing called a vector. Now, in the IT industry, we love to invent brand new words for the same old technology. We have the terms vectors and tensors, etc. But all these things, what are they? Well, a vector is just a list of numbers. We talk about it as being the fundamental data structure when it comes to artificial intelligence, but in its simplest form, a vector is just a list of numbers. And people say, well, hold on, that's not new. Every programming language you've ever thought of has had the support for concept of arrays. Even back in the day when I was a child, I had an old Commodore 64. Even that with its basic programming language had arrays in it. So there's nothing new about vectors besides the name. It literally is just a list of numbers. And the key point is not about what the vector structure is. The key point of why this AI stuff is so impressive is you can map data to a vector. And the key thing is you can map any data to a vector. You can map text, you can map numbers, you can match images, audio, PDF files, any form of data you can think of, XML, JSON, whether it's structured, whether it's unstructured, whether it's huge, whether it's small. Any form of data can be put through some sort of processing and then come up with a list of numbers. Now, people say, well, hold on, that's not new either. I'm sure every time you've downloaded something from the internet, like a piece of software, you often see like it says, oh, here's the MD5 hash associated with that zip file. So the concept of having a number associated with complex data is also not new. It's just like hash functions. So we still haven't seen anything brand new here. We've got a list of numbers, that's just an array. We've got the ability to map data to a list of numbers, that's just similar to hashing. So maybe the magic of this AI and vectors is maybe for more abstract data. But even that really isn't that new. I think we can assume something like the color purple is relatively an abstract data. It's something that we don't store typically in a database. Yet for decades, we've had a mechanism of representing something abstract like color as numbers. As we know, if you've ever used a computer monitor, you know that color is represented by typically RGB. Effectively three numbers, in this case 25% red, 50% green, and 75% blue, to represent the generation of the color purple. So even this is not new. I'm just talking about color television here. So having said all that, what is the breakthrough? If vectors aren't new because they're just a list of numbers, if mapping of data to vectors isn't new because it's just hashing, and representing abstract data as numbers isn't new, it's like colors and RGB, what is the great breakthrough? Well, I hate to say it, I hate to be cynical, but fundamentally it's about money. And that money has been funneled into the following area. Giant farms of GPUs with weeks or months of compute time, spending literally billions of dollars in compute cycles, electricity, cooling, etc., to convert data into vectors. And the magic is not the fact that we can convert data into vectors, it's the fact that those vectors have a special relationship to each other. Before I talk about that, one of the beauties of mapping data into just a list of numbers is you get incredibly dense compression of information. I might have 10 terabytes of data, but when I put it through these giant farms, I might end up with a file which is only 100 gigabytes in size. So I think of vectors as like WinZip for human knowledge. I can take abstract concepts of data, vast volumes of it, put it through a giant GPU farm, do lots of processing, modeling on it, and come up with a list of numbers at the end of it, which is far smaller. But the key thing is that far smaller number still preserves the original meaning of the data. And we'll do a demo later on if we get some time to show you that it is amazing that just a bunch of numbers can somehow still capture the meaning of the source data, even if that source data was a picture or a Word document or images or video, etc. Just you think you must lose something if you convert that information just into listed numbers, but we'll see later that it doesn't. The way of thinking about a vector is, I like, in terms of describing how it's built up, I think about it like a point in n-dimensional space. A vector being a list of numbers, we can think about it as basically a point in n dimensions. Now, obviously describing things in n-dimensional space is a non-trivial task. I certainly can't draw any diagrams like it. And for the rest of this session, I'll use a metaphor. If I was trying to give you directions for how to get from one city in India to another, I might give you something in Apple Maps or Google Maps, etc. Now, Google Maps is 2 dimensions. The real world is 3 dimensions, but we don't give people instructions in 3 dimensions. When we need to simplify topics about a complex number of dimensions, in this case 3 dimensions, what do? We reduce the number of dimensions. I don't give you street directions in 3 dimensions, I give you to them in 2 dimensions because that's good enough and makes the understanding simpler. I'm going to do the same for vectors. Vectors typically are in 500 dimensions or 1,000 dimensions or 768 dimensions. But throughout this, we'll talk about vectors in just 2 or 3 dimensions because it makes the discussion much easier. But in reality, remember that vectors are actually in n-dimensional space. So what happens is we take some data, and I've chosen some very simple data here. My dogs join me. Hello. I've taken some very simple data here, the words dog, cat, kitten, and puppy. I've put them through some sort of processing model, and out comes a list of vectors. As I said, just numbers that represent the meaning of that data. If I was to draw those vectors in 3 dimensions, even though in reality it's a lot more dimensions, it might look something like this. Cat might appear somewhere up the top right here. And if I then drew the vector for where kitten is in 3 dimensions, it might be slightly down and to the right. The magic of these GPU processing models is where these vectors sit in n-dimensional, or in this case 3-dimensional space, represents the relationships between the data. So when I do the vector for dog, it might land, say, here. But because the relationship of a kitten to a cat is the same as the relationship of a puppy to a dog, we would expect puppy to land somewhere here. In the same way that kitten is slightly down and to the right, puppy will be slightly down and to the right of dog. And what's more, when we process lots of data, we establish effectively a trend. Any kind of relationship in the data we pass through these models that might be, say, father to son, might be grandparent to mother, etc. Anything which is a paternal or parental kind of relationship will follow this sort of direction, up and downwards to the right. So not just dog and cat would map this way, but anything that represents some sort of paternal relationship would actually look this way. So the vectors capture the meaning of the data, even though we're only plotting it in 3 dimensions. Now, it seems a big jump to go from, hey, I can just grab vectors and plot them in n-dimensional space, and somehow out comes ChatGPT. That seems a big jump to make, because ChatGPT almost seems like we're talking to a human at the other end. But in reality, the mechanisms are actually very similar. If I was to say to this audience, if I was standing there live and I said the World Cup winner will be, or is, I would imagine that almost everyone would basically shout out, it's going to be India. Congratulations, each of you has just acted like ChatGPT. You took a series of words, the World Cup winner is, and your brain said, what's the most likely next word to put in there? And you came up with India. That's how effectively ChatGPT works. You take a sequence of pieces of data and use that data to predict what the next data in line should be. Effectively, we're looking for common patterns in the data to predict what the next word will be. And the obvious question is common patterns of what? Because we can't just say it's going to be words, because as I said, we can put images into these algorithms. We can put sound into these algorithms. We can put any kind of abstract data. To standardize that, we go through a process what's known as tokenization. And tokenization is effectively an algorithm or mechanism to break up complicated data into small pieces, which can then be converted to vectors, and then we can use those vectors to predict what should come next. So you can actually play with this yourself. If you go to tokenizer.vercel.app, you can actually type in, for example, a piece of text, and based on certain algorithms, like in this case at the top right, you can see CL100K base. That's a certain algorithm used to break up English language into tokens. You can see the World Cup winner is India as a sentence. When we break it into tokens, would be 9 tokens. And we can see there at the right, it says the World Cup winner got broken into 2 tokens, win and ner, and is, and same thing, India got broken into 2 tokens, Indi and IA at the end. So often it's just the word itself, But there's a whole science and academic field of study behind tokenization. There are different tokenization algorithms. You may have heard of one called sentence speech, which is Google's one. But there's lots of different tokenized algorithms which take some source data, in this case it's English language, and break it up into small tokens. And each of those tokens then gets put through a model to then generate a vector. So it might end up looking something like this. The World Cup winner is, and I've broken each of these tokens into vectors. Now, how do we take those vectors to come up with a mechanism of predicting what the next word will be? Well, probabilities get used to predict the next token. And before AI really sort of took off in the last few years, AI isn't something new. It's been around for 40, 50 years. Back in the 1950s and 60s, they were talking about artificial intelligence then, and all they were doing was using probabilities. So take a whole lot of English language, put it into an algorithm, and come up with a probabilistic algorithm to say, when I see the following sequence of words, use the probability of what the next word will be. These things actually weren't that good at doing that. So basic probability wasn't enough. And in reality, and that's what made AI sort of leapfrog forward very recently, is it's a little bit more complex. They become inputs into a neural network. Now, what's a neural network? To help describe that, I'm going to use a simple metaphor. I'm sure you've all done this at some stage in your college or high school life. You've got a sequence of points on a graph and someone said, go put a line of best fit on there. Now, as you could see from that little video there, nowadays we just stick it into Excel or in some kind of charting tool and we simply say, give me a line of best fit, give me a regression line. Nice and easy. We don't have to understand the formula behind it. But you may remember from back in high school days, there was actually a formula. If you had a series of dots on an XY axis, there was a formula. I think you added up the X values all squared, added up the Y values all squared, you multiplied them together, and you put them, there was a known formula you had to do with square roots and all sorts of things. And at the end of it, it would give you M, which is the gradient of the best line, and the Y-intercept. And so there was a way of actually working out what the line of best fit was because there was a known formula. If you know a formula, then obviously solving problems is very easy to do. You just apply the formula to the data and out it comes. When you think about something like predicting the next piece of text, well, there isn't really a formula for that. So let's continue with this linear regression or line of best fit example, but let's say we lived before the mathematicians of the 1600s, and so there was no formula. How could I work a line of best fit out if I didn't know the formula? Well, one option I could do is tackle it almost in reverse. Rather than try work out the line of best fit, I'll just throw any old random line on there. In this case, you can see I took a random guess. And that's maybe a reasonable guess. It's not really great. You can see there's a lot of dots nowhere near the line. But because I don't have a formula, I can start just with a random guess. But what I can do is now I want to improve that guess. Now, in order to improve the guess, I need some way of measuring how good I think this particular guess is. Now, I'm just making up an invention here. Whatever algorithm I come up with doesn't really matter as long as it's consistent. For me, I've said what I'll do is I'll measure the distance between each dot down to the line or above to the line, and I'll add up all these numbers. That gives me a score. How good is this line? Then I'll take a random other guess. Let's take another guess. And I'll do the same thing. If they add up the score, if the score for this one is better than the previous line, then I can assume that this line is perhaps a slightly better fit. It's not perfect, but it's better. If the score came out worse, I would say let's go back to the original one and maybe shift the line in a slightly different direction. But I'm effectively, because I don't have a formula, I'm just taking guesses now. But each time I take a guess, I do some sort of measurement to see, is my guess getting better? So I measure this one and I maybe adjust it again, and then I adjust it again, and I keep measuring to see, hopefully getting slightly better. Sometimes I'll go in the wrong direction and I'll come back, etc. But eventually I get to a point where no matter what I do, if I move this line, my score gets worse than this particular score. At that point, I've reached effectively an equilibrium point. And now I have the line of best fit, even though I never had the formula to work it out. I started with random guesses, and slowly by iterating over and over and over, using some sort of scoring mechanism, I could arrive at the line that best suits my results. That's how we can solve problems when we don't have a formula to solve them. I can start with a random guess and slowly improve that guess over time through a lot of iteration. And that's exactly how these models work when it comes to solving the problem of what word should come after the World Cup winner is. There is no formula for that. So what happens is these all become inputs into what we call a neural network. All these tokens become vectors. The vectors get passed into this giant model, which is really just doing similar to our line of best fit regression thing. It's taking effectively these vectors, applying weightings to them to come up with what the next token, the next vector should be. So it goes through all this neural network, and effectively these neural networks are just simple mathematics. Vectors are just numbers. So these numbers in yellow here are just weightings, effectively random numbers we originally generated to apply weightings to our vectors to come up with what the next vector should be. So literally these neural networks are just big, huge sums of relatively simple mathematics doing matrix operations on these vectors, and out comes these numbers, and they get feed-filled into the model further on. So what happens is all these tokens get fed in, it goes through this big model, and at the end out comes a vector. And we are hoping that vector corresponds to the token for India, because that's the next vector we want to see. And the first time we run it through, we're expecting to see India, and we'll probably see something like avocado or some other random token. You're going, where did avocado come from? Well, think back to our linear regression model. We took a random guess to start with. Our first guess was not a great result. These neural networks are the same. I feed in my vectors, I put them through a lot of algorithmic processing, and out comes a vector at the end. If it's not good, I then change the weights, change the algorithm slightly inside that neural model, network model, and run the processing again. You can start to see where these GPUs are required for all these huge amounts of computation. So what happens is, over time, each time I run this model, various words may come out. Now, the first time I run it, it might say avocado is the most probable, that's the best result, like our bad guess at linear regression. But then I adjust the weightings and I go run the model again, and it says, oh, this time India became slightly more likely. These ones are still relatively highly probable, and we don't want that. We want the model to be trained such that it always comes out probably with India. So we run the model again, and over time, the probability of choosing avocado or sheep or jalebi all drop to almost zero, and the probability of choosing India becomes extremely high. Once we've done that, we know that the weightings in this model, just like we adjusted our random linear regression line guesses, will actually model that these weightings are actually very accurate for predicting the right word. Now, in reality, it's actually way more complex even from that, because I said to you the World Cup winner is, and hopefully you all guessed India, but there was a bit of a context here. There's a base knowledge in the room. Because I'm doing this talk obviously to a group of people in India, and cricket is obviously the big sport in India, you've all assumed I'm talking about cricket. So there's a context. Effectively, there's a base set of assumptions and memory that you are all applying to that sentence. Right? The reality is, I might have been talking about the Soccer World Cup. Now, for that, the answer probably wouldn't be India. It would be Brazil. If it's rugby, it would probably be New Zealand. If it's skiing, it would probably be Austria. It very much depends on the sport. And that sport I never mentioned, but it was effectively the context. In this room, in this auditorium, I know where, it's an Indian audience. We all love our cricket. I'm the same. I'm from Australia. Australians and Indians all love their cricket. I'm probably talking about cricket. So the context, the background, the assumptions that we make are very important in terms of predicting what the next token should be. And that's the big thing that really changed AI in the world in the last few years. The understanding that it's not just a case of grabbing tokens and doing probabilities to guess what the next token is. It's more than that. You need to understand that there are relationships between the tokens. The fact that the World Cup is referring to cricket, for example. We need to understand those relationships. And this was a big landmark paper. I can't remember when it came out, maybe 2019, I think, from some people from Google. This concept of attention is all you need. The concept of understanding that it's not just a list of tokens that are vectors. We need to actually understand relationships between them. So in its simplest form, I may have taken, for example, I've deliberately inserted the word cricket here to help explain this example. I may have taken this sequence of vectors, right, and it came up with something like this. But the important thing is, once we start understanding the relationship between the vectors, that there's a relationship between the word cricket and world, then that might generate a different vector. So without understanding that relationship, the word that comes out might not be India, might be New Zealand or Austria, or etc. But once we understand there's a relationship between the token for cricket and the tokens for world, etc., then it might give us a slightly different vector that comes out of our model, therefore generating the word India. You can think of it this way. I'll go back one slide, sorry. Let's go back one. Also in there is the token for cup. The vector for cup may sit here in isolation. If I just say, give me the vector for the word cup, it says, oh, yep, it's somewhere up here in three-dimensional space. But when it relates to tokens around it, like cricket and world, well, we're not talking about this kind of cup anymore. We're talking about the Cricket World Cup. It's a totally different cup. So it's the same word, the same token, but it actually should be a different vector because it has relationships to the tokens around it. So hopefully that three-dimensional model explains how we adjust the vectors based on the context of other vectors around it. So what happens is, in ChatGPT's case, it's even not just as simple as that. We take all these tokens, and what happens is they go to what's called an attention model, which is the thing that's looking for the relationships between the tokens. That information gets fed back into the model called a feed forward, and we repeat this exercise many, many, many times. And eventually out pops India. The original version of ChatGPT, I think, did this 20 iterations. And don't forget, we're doing this not just on one sentence, we're doing it on literally terabytes of data. We've scraped the entire internet. So you can imagine how much GPU processing is going on here. And that's why it's actually so expensive. But the good thing is, it's not just going to be about code. Most of us, when we think about AI nowadays, especially as students, we're thinking about things like Claude and Codex, the ability for it to generate code on our behalf. It's also going to be very cool for data, which is very nice. Let's go back to my simple RGB model. Remember I said we can map abstract colors as vectors as well. So I've got red, green, and blue in 3 dimensions here. If I draw this color, which is 75% red, 10% green and blue, I go 10 out, 10 across, and 75 up, and that's where it lands in 3 dimensions. If I draw this color, which is 50 red, 70 green, 70 blue, we go 50 out, 50 along, and up 50, and there we get that one. This next one is 25% red, 75% green and blue, so along 75, out 75, up 25, and we have 3 colors. You can see that obviously 2 of these colors are very similar, and they're not very similar to the red one. And the beauty of vectors is, notice that the relationship between the data is also represented by the distance between them. These 2 are very close in 3 dimensions, and they're similar colors. These 2 are not similar at all, and they're a long way apart. The magic of these vectors, once they've been processed by these models, is that the distance between vectors represents the similarity of the original data. Now, how do we calculate distance? It's good old-fashioned high school mathematics. Do you remember, probably if you're calculating distance between points in 3 dimensions, you drop a line to the perpendicular, create a right angle, and you do all that Pythagoras kind of stuff. X squared plus y squared, take the square root of the hypotenuse, etc. It's literally basic high school maths to work out distances. An alternative way of working out similarity would be to look at the angles. If the angle between these 2 things is very, very small, then we can assume they're fairly similar. If the angle's very large, then they're not similar. And luckily, once again, high school mathematics tells us that if I use cosine of a very small angle is a large number, cosine of a big angle is a small number. So the cosine of the angle also gives us a measurement of how similar these vectors are in terms of the original data. At which point, it's just good old-fashioned high school mathematics that underpins all these amazing AI models. What this means when it comes to processing data is we have some really cool facilities where we can now say, if I take pieces of data, I've just chosen some simple words here, and plot them as vectors, I've made it very simple, just 2 dimensions here, then where that data lands in 2 dimensions represents how the data is related to each other. So for example, all the animals are sort of clumped together at the top. The fruits here are clumped at the bottom left and cities are clumped at the right. If I was to bring in the word tiger, it would probably land somewhere here because a tiger is bigger than a lion, so it's closer to an elephant, but it's obviously related to the cat family, so it might land somewhere about there. Where vectors land in two-dimensional, or in reality, n-dimensional space, represents the relationships between data. And then applications can use that information. Here's a real-life example from a website here I use regularly in Australia. It's a hardware website, and if I type in I want to buy a lawnmower, it gets me lots of hits. But if I type in I want to be able to cut some grass, and obviously cutting grass is what I would use a lawnmower for, it finds no hits. It doesn't understand that cutting grass, the human meaning of cutting grass, is the same as using a lawnmower. Obviously, in terms of the actual data, the word cutting and grass has no relationship to lawn and mower, just from a pure character point of view. But in terms of actual human meaning, there's a relationship there. And for that reason, we can use some nice things. So let me show you a little demo of this in action, of where these vector processing might be really useful when it comes to dealing with data. So just to give you an example, I'm using an Oracle database here. I don't want to go too much into the features, but the Oracle database lets you build vectors simply passing an array of numbers. So that's a vector of 7 dimensions. And as I said, just like high school mathematics, vector distances are very important when understanding the relationship between data. So there's a vector at 1, 1 in 2 dimensions. There's a vector at 3, 1. Hopefully your high school mathematics is remembered. You know the distance between them will be 2. And here we go. Distance between these two vectors is 2. Let's see now this in action. I've got a table here full of trivia. It's got 330 rows of useless pieces of trivia. Just to hone in a little bit on what's actually in the table, I've got some information about cities in the USA, information about cars, information about fruit, information about dogs, and information about alcoholic beverages. Here is an example of where vector processing for data is very, very powerful. Someone might come along to a website that exposes this data and says, I'm looking for information about nutrition. And our application says, I'm sorry, I don't have any information about nutrition in there for you. So how about diet? Nope, not in there. And the reason this seems to fail is because it's literally doing a keyword search. It's trying to find the word nutrition in my set of data here. And the word nutrition doesn't appear, the word diet doesn't appear. However, the fact that there's information about fruit in there, well, maybe there are some nuggets of information about good nutrition in this data. Just because the words don't appear doesn't mean the data is useless. What I need to do is find the relationships between the data, the ones that map closely to the concept of nutrition and good diet. So the way I can do that is I can load up one of these vector models. This model here is designed to understand the meaning behind human language. Then what I do is I actually create what's called a vector embedding, which is take all those pieces of trivia and convert them to vectors, because where those vectors land in n-dimensional space represents the relationship. So now for every piece of trivia I had in that table, I've now got a vector that represents the original meaning of that data. Now, vectors are actually huge. I've truncated these so they look a bit nicer on the screen. But if I'm going to see which of these vectors, which relate to the source data, relate to nutrition, then I need the vector for the word nutrition. So I'll take the words good nutrition and say, give me a vector for that. This will show you what vectors really look like. That's what a vector really looks like. So each of these vectors up here are also huge numbers, huge list of numbers, but I truncated them just to keep them on the screen nicely. But that's what a vector really looks like. But if I've got the vector for all my pieces of trivia about cars and fruits and dogs and cities in the USA, and I've got the vector for nutrition, then whichever vector is closest to the vector for nutrition is probably about, hopefully, about something that's going to talk to me about being healthy. So I go get all the vectors in my table, compare it to the vector for good nutrition, find which ones are closest, and out pops this. This is the power of vectors. It sort of has captured the essence of the meaning of the data, not just the raw data itself. So the word nutrition never appeared in my table. However, it could work out that this information here is related in some way to nutrition. So it's pretty cool. I look for things like Suzuki, and it found information about cars. I look for information about the fastest running dog, and it found information about greyhounds and domestic cats because I had some speed information. But we get an idea for how powerful this is because these vectors, even though they're just numbers, where those vectors sit in n-dimensional space somehow represents the relationships between the data. And we can do it with any data. That's the beauty of this stuff. I could take raw data and turn it into vectors, but I could take medical history if I'm building something that's going to basically give me medical advice. I could take it with code. That's where Codex and Claude and Cursor and Copilot come from. I could just trawl the internet, and that's where things like ChatGPT come from as well. Another challenge is if I'm taking all this abstract data, plotting it into n-dimensional space, how do I find stuff in it quickly? Let's say I took a picture of every single person in the auditorium, turn them into vectors, just three-dimensional vectors. So you can see here, here's a picture of everyone in the auditorium in 3 dimensions. Who is the poor, unfortunate student that looks most like me? I would have to compare my picture, the vector, to every single other vector. I would have to find the distance to every single other vector in 3-dimensional space in order to find the closest one. That's very expensive. To solve that, we have a thing called vector indexes. And to give an example, that is, if I'm trying to find the nearest city to, say, Bangalore, I would have to do the distance to every other city in India. That's very expensive. What I could do to make it more efficient is carve up the data into states. I'm using Indian states here. And then all I have to do is pick, for example, the 3 closest states and do a brute force search in there. So if I can carve the source data up into chunks and then dig into just a small number of chunks, I get performance benefits. The question is, how did I arrive on picking just these 3 states? Why didn't I pick one of the other states? Well, the way these things work is when we're building these structures, we calculate the midpoint of every single state. Each chunk of data gets assigned a midpoint, and then we simply choose the 3 closest midpoints. So when I'm looking for the city closest to Bangalore, I go check the distance from each of these yellow dots to Bangalore. That's going to be, say, 30 or 40 checks. Once I found the 3 closest ones, then I can do the brute force search just in there. Now, key point, you have an accuracy cost trade-off here when you start doing this, because this state here, that's a very big state. It may turn out that the midpoint for this state down here is actually closer. I could actually pick these 3 states to look through and literally miss the state that Bangalore is in. I might actually miss the closest city. So these techniques for finding vector information quickly also come with a risk in the fact that you might not always get the correct response. But I've got a few minutes left. I want to wrap up. One of the cool things is if you want to play with vectors, there are lots and lots of really cool, very simple free resources. One of them, if you're running Windows or Mac, LM Studio is a piece of free software. It lets you run an LLM on your own machine. You don't have to go talking to ChatGPT or Gemini, etc. And one of the beauties of running it locally is, A, for a start, you're not giving